Okay.
Okay, welcome back, everyone. So for our second talk, we have Kathryn Hess, who's going to tell us about a shadow perspective on equivariant Hochschild homologies.
Okay, thank you very much, JD. Thank you for the invitation to speak today. So the work I'm going to be talking about is joint work with Kathryn Adamek, Tina Gerhardt, Inbar Klang, and Hannah Jiakong that started at the third Women in Topology workshop in 2019. And that led to a couple of articles that have appeared in the past year. So I'm going to start by talking about twisted THH of CN spectra, which was the motivation for what we did later in our second paper. So this is the original definitions here go back to a paper by Engeltveit, Blumberg, Gerhardt, Lawson, and Mendel from 2018, where they're thinking about what is the right way, what is an interesting way to define a twisted version of topological Hochschild homology for equivariant ring spectra, in the case where you have a cyclic group that's acting. So suppose that R is a CN ring spectrum or an orthogonal ring spectrum, just to fix precise the framework, and let's let M be an R bimodule. So a spectrum that has an R bimodule structure. And from this data, you can build a simplicial spectrum that in its qth level is just, get my picture here. So in the qth level is just have M and then you have smashed with the smashed copy of R copies of R. Q copies of R, sorry. And so what are the face maps here? And this is where the twisting is going to show up. So the zeroth face map is just given by using the right R action of R on M. The I space maps for I between 0 and Q are just given using the multiplication in R. And the last space map is different from what you would usually get in the cyclic Barks instruction, in that you're going to take the last copy of R over here, and you're going to use the left R action on M to do it. But first, you're going to twist by this action of Cn. So you just act on Cn with the generator, act on the last copy of R with the generator Cn, and then you make that act on the left-hand side of M. So you use this twisting that takes advantage of your Cn action. And if you then take the geometric realization of this simplicial spectrum, you get the Cn twisted topological Hochschild homology of R with coefficients in M. So this is a model for the relative norm of R. In this case, in the case when M itself is equal to R, that's why this was first developed. And so this gives us the natural CN spectrum structure itself. And in the case when M is R, with its usual R bimodule structure, then you actually have an S1 spectrum because you actually get a cyclic object and not just a simplicial object. So you can ask, well, this is something that's nice and important because we're talking about norms in this case, but how can you compute it? So what we did in our first project was actually to provide a tool in order to be able to do some computations of this twisted topological Hochschild homology. So we developed an equivariant version of the usual Bergstedt spectral sequence, which gives us a way of computing the homotopy groups of THH. So let's suppose that we have G, which is a finite subgroup of the circle. So we want to, I'm just going to take an abstract cyclic group. I'll actually think of it as living inside the circle. This is a finite subgroup with some generator G. And we'll take R to be an orthogonal G ring spectrum. And E is going to give us the cohomology theory we want to, with respect to which we want to work. It's going to be a commutative G ring spectrum on which this little generator acts trivially. In this case, we can set up a spectral sequence for computing this Hochschild homology. So in the case where now we're going to look at the ROG graded commutative ring functor that we get by applying the Mackey functor to the smashed product of these two spectra. This is going to give us an ROG graded commutative green functor. If this thing is flat over the coefficient ring, then there exists a strongly converging spectral sequence of Mackey functors in this case. From here, I'll explain what this is in just a moment. So something that is purely algebraic to the E homology of, well, here we have this G-twisted topological Hochschild homology of this orthogonal ring spectrum, R. And then since we did, this is just with R, we're not taking coefficients in any module, then this thing actually has a circular structure, and we pull it back to looking at it just as a G spectrum, and then we take the homology of that. So this gives us a tool for computing the homology of this thing. And what this algebraic input to the spectral sequence is a version of Hochschild homology now for green functors. So here, there was work done by Blumberg, Gepner, Hill, and Lawson that developed a theory of Hochschild homology for green functors. And we just generalized it somewhat to thinking about algebras over this ROG graded algebra. And in this case, it's a very similar sort of construction where you do a cyclic bar, you do a cyclic bar construction, and then you can take the geometric realization that gives you now an algebraic object that you can compute. And the idea is this should give you something you can actually compute in the E2 term with a bit of luck. And with a lot more luck, you can actually compute the differentials, and in the end, figure out what you get for the homology of this G-twisted topological Hochschild homology. And it turns out that the spectral sequence does actually really enable us to do some computations. But before I show you the result of a particular computation, just want to point out that so we have here, as I said, a spectral sequence of Mackey functors. If we evaluate these Mackey functors at the trivial subgroup, then we actually recover the classical Berkshire spectral sequence in the case where you're looking at Hochschild homology with coefficients in this algebra seen as a twisted bimodule, twisted with respect to this action of the generator of the cyclic subgroup. So you can recover the classical Berkshire spectral sequence. And in the case when your original ring spectrum is actually commutative, then you get a spectral sequence of algebras and not just of Mackey functors. So it's possible to use this spectral sequence actually to do some computations. And here's an example of a computation that we did for the real Bordism ring, and have a very explicit computation here where the degrees of all of the generators of both the polynomial part and the exterior part, where here rho is a regular representation of C2. So this is just one example of a computation one can do. I'm not going to go into the details of how it was done. But then one question that I found intriguing, we decided to work on is, so what are sort of usual properties of Hochschild homology that are important, such as Morita invariance, which I'll recall, such as agreement, which I'll also recall, hold also for this twisted THH. So because you'd like to know that it was sort of part of the same kind of family of theories. And so wanted to try to investigate those questions. And the way we decided to try to investigate them was to try to move this study of twisted Hochschild homology into a more general context where these sort of properties were known to hold. And so that's what I'm going to talk about now, this more general abstract framework in which one has a notion of Hochschild homology for which one is sure that these desirable properties actually hold. So this is the notion of shadows on bicategories, of which Hochschild homology is the prime example. So I'm going to just set up some basic language here. I'm going to work in the context of bicategories. If I have a bicategory B, it's specified by its collection of zero cells or objects. So here are my zero cells A and B. By its collection of one cells or morphisms, which I'll note M and N because I'm thinking about modules. And then the two cells, which are morphisms between the morphisms. So this is the basic structure of a bicategory. But in addition, what we know is that if I have any two zero cells, then I actually have a category of morphisms. The objects in this category are one cells, and the morphisms in this category are two cells. And I have, for any triple of zero cells, what's called a horizontal composition functor that'll take from the category of morphisms from A to B, category of morphisms from B to C, and produce a morphism from A to C. And this composition should be appropriately associative up to isomorphism two cells and unital with respect to sort of distinguished unit objects. So within this category here, I have an object that we'll call UA, which is a distinguished unit object. Now, here's an important example of the category of a bicategory that I'll call ring. So in the bicategory ring, the zero cells are associative unital rings. And the category of morphisms from an associative ring A to an associative ring B is just the category of AB bimodules. And in this case, the unit object is just A seen as a bimodule over itself in the usual way. And the horizontal composition is, well, you make some choice of what you mean by tensoring M and N over B. And this is where things are only going to be defined up to isomorphism and so on. There's a question in the chat. Let me just see. Do I mean for these morphisms to be in the opposite directions? No, I don't, Doug. I'm really thinking about, I'm thinking here about this. This is an AB bimodule, and I'm really thinking about it as a morphism from A to B.
Okay,
And,
so
yeah.
In a previous slide, you had the two cells. You had a little diagram for the two cells, saying what two cell was, and your two morphisms were going in opposite directions. That's why I asked the question. Right.
Oh, so one of them was going from A to B, and the other was going from B to A.
Yeah. Is that what you meant?
I believe so. In the previous slide, I would have to go back. But in this case, this is really the way that I mean for things to be. And then we're going to be interested in a generalization of this, where I'm going to consider some sort of nice enough monoidal model category. So nice enough meaning it was, in particular, monoidal model category, meaning we have an induced tensor product on the homotopy category. And nice enough, well, most of the monoidal model categories that we care about would be nice enough in my context. I'm not going to specify what that means, but it's going to include things like symptotial sets and the categories of spectra we care about and chain complexes and so on. So what I'm thinking about is a bicategory in which the zero cells are now going to be monoids in this monoidal category. And I'm going to pose a condition that the underlying object in the category V is actually cofibrant. And then the category of morphisms between these guys is going to be the homotopy category of the category of bimodules. So one thing that's hidden in the definition of nice enough monoidal model category is that there's an induced model structure on the category of AB bimodules. And so that it makes sense to talk about this homotopy category. And by the way, this example is generalizing an example. It's in a paper by Campbell and Ponto, where they were talking about the case when V is the category of spectra, some metric spectra or orthogonal spectra. Again, the unit object is just going to be A seen as a bimodule over itself. And now this horizontal composition is going to be derived tensor product instead of actual tensor product that I'll get by explicitly the choice that I'll make is to take a bar construction, the two-sided bar construction with coefficients in M and N, and then taking the geometric realization of that. And it turns out that because we're working, everything is nice enough and these guys are cofibrant and everything, that this is actually going to give me a full bicategory structure. So the notion is going to be important for us in the context of bicategories. So there are going to be various notions related to duality. And this is one reason why we're going to care about shadows, because what their relationship is to these notions of duality. So I'm in my bicategory B, and I have a couple of zero cells A and B. And so what is a dual pair in this case? So here are my couple of zero cells like this. It's going to be a pair of one cells, M and N, like this, together with some two cells that go between, first of all, the distinguished unit object on A and the composite MN. So I do MN, I end up back at A, so this is an AA object. And similarly for B, I'm going to have some sort of two cell from N, the composition of N and M, to the unit object on B. So if this looks a lot, you think this looks a lot like an adjunction, you're right. If I consider the bicategory, which is the category of categories, then a dual pair is in fact precisely an adjunction. So this is the data that we have in adjunction, and we require that it satisfies certain triangle identities of the usual sort. So here's my picture again of a dual pair. And so one of the triangle identities says, well, if I start at N and then I use eta to go into N composed with N equals with N. So my associativity tells me that this is going to be isomorphic to this. And then I can use the epsilon to reduce that. And I get down to N. And here I'm actually suppressing some of the unitors in the story. But anyway, this thing should commute. And similarly for M. So that's the notion of what it means to have a dual pair for A and B. And in the case when this dual pair is actually such that both epsilon and eta are isomorphisms. And if I now put things in another order, n, m, and then the inverses of these guys, it's also a dual pair, then it's what's called a Morita equivalence between A and B. And we'll say that A and B are Morita equivalents if there is such a Morita equivalence. And we'll in our context that we cared about. So in the case, for example, when we have a dual pair in the bicategory ring, the existence of a dual pair like that means that we actually have an adjunction of the type you would expect, going between the categories of right A modules and right B modules, where we use 10 string over A with M or 10 string over B with N, and this gives us an adjunction. Okay, and there's something similar that happens in the context with in ring V, and if it's actually a Morita equivalence in this category ring, then it's going to give us an equivalence of categories like this. So the existence of a Morita equivalence in this formal sense that I just defined it really means that A and B are Morita equivalent in the usual sense of the word. Okay. So, and it turns out that there's an analogous result in this category ring V, where instead we'd be saying we end up with an equivalence between the homotopy category of mod A and the homotopy category of mod B when two objects in ring V, two zero cells in ring B, are actually Morita equivalent. So this all sort of fits as we would expect. Okay, so shadows now. Now that we know what we've recalled what bicategories are and these notions of duality and Morita equivalence. So suppose we have a bicategory B and a category C. So what is a C shadow on B? So it consists first of a bunch of functors. For every zero cell in B, we have a functor from the endo category of morphisms from A to A and the two cells between them to the category C. So we have one functor like that for every zero cell. And then a bunch of natural isomorphisms between the following. So if I take this particular composite here, M tensor N, then I have an object in this category here. And so I can apply sigma A to it. Or if I take the tensor in the other order, now I have an object that's in BBB, and I can apply sigma B to that. And it turns out, I mean, the structure that you need for this thing to be a shadow is to say, oh, these things are actually naturally isomorphic. And what we see is that what this is saying is that this trace, there we go, this shadow has a very trace-like behavior. That at least once you look at the images in the category C, you don't really see a difference between the shadows of M tensor N and of N tensor N. And then there are various axioms that have to be satisfied, various compatibilities and so on, to get compatibilities with the associators and the unitars that one has in the bicategory. So what's the relationship between duality and shadows? So if here I have one of these dual pairs, we can make the following construction. We can start with looking at the shadow of the distinguished unit object from A to A, use eta to go into the shadow of M tensor N. Here we use the natural isomorphism theta AB that tells us that this is isomorphic to this. And then we can use the shadow of the epsilon map that goes from N tensor M to the unit object on B. So this gives us together a map from the shadow of the unit object on A to the shadow of the unit object on B, which for reasons that have to do with specific concrete examples, Kate calls the Euler characteristic of this dual pair. And if this is actually a Morita equivalence, well, in the case when this is a Morita equivalence, then epsilon and eta are both isomorphisms. And since the sigmas are actually functors, this will be an isomorphism and this will be an isomorphism as well. And so the whole composite will be an isomorphism. So what it tells us is that if this dual pair is actually a Morita equivalence, then this Euler characteristic is actually an isomorphism. So it's telling us that anytime we have a shadow, we have Morita invariance of a certain sort. And we'll see that this translates actually into the Morita invariance of Hochschild homology in the particular cases that we care about. And there's a more general formulation of this that one can get into as well when you want to think about coefficients and so on, but this is the basic version. Okay. All right. So the most important examples of shadows for us are Hochschild shadows. So let's call it VHH, the generalization of THH. So let's take a nice monoidal model category again. Let's start with a zero cell in the category ring V. That is to say a monoid in V whose underlying object is cofibrant, and an AA bimodule. So we can do a cyclic bar construction using A and M. So this is going to give, here I start with a simplicial object that in level N is the iterated tensor product of A with M. And as in the previous case, the face maps are coming from the multiplication in A, the left action of A on M, and the right action of A on M. But here, where we again use a cyclic permutation to move the first copy of A around here, but we're not twisting it now. We don't have any cyclic group actions or anything like that by which we could twist. So it's just a standard cyclic bar construction, gives us a simplicial object, and part of being a nice enough monoidal model category is that I have some appropriate notion of geometric realization so that I can geometrically realize this simplicial construction and end up with an object in V. So the Hochschild homology, the V Hochschild homology of A with coefficients in M is now going to be an object in V. And if you're just going to take coefficients in M, where M is now A, seen as a bimodule over itself, we'll just simplify notation and call that the V Hochschild homology of the monoid A. So this, in the case where V is an appropriate category of spectra, and this is the smash product and so on, this gives us THH. Straightforward generalization of THH. And it turns out that this thing is actually a shadow. If I look at this collection of functors, okay, so this is ring VAA, this is the endomorphism category of one of these objects A. And if I look at the functor that is HVVA, and then here I can plug in any AA bimodule, that's going to give me something in the homotopy category of V, an object in the homotopy category of V. And it turns out you can actually equip this with a structure of a shadow on the bicategory ring V, whose target is the homotopy category of V. And what's missing to have a shadow here, you need to have the sort of trace-like property of the shadow. So with the existence of these natural isomorphisms, these thetas that I was talking about. And the existence of these thetas is coming from something that's called the Dennis-Morita-Waldhausen argument, because what you need to look at in that case, you're having a sort of a bar construction of a bar construction, sort of looking at it in two different ways, sort of horizontally and vertically, comparing these bisimplicial objects, and you want to, the comparison you need to make in order to get the isomorphism that you need for the shadow really has to do with the fact that you can do it horizontally then vertically, or vertically and then horizontally, and you get the same thing. So that's this Dennis-Morita-Waldhausen argument that gives you the thetas you need, these natural isomorphisms, in order to get a shadow. So you have, in this case, a nice shadow. And because it's a shadow, you have Morita invariance. If you have two monoids in this category V, at least as long as their underlying objects are cofibrant, and they're Morita equivalent, so you're getting you have this equivalence between the homotopy categories of modules, then their Hochschild homologies are isomorphic. So anytime you have a framework in which you can set this up, you know that you're going to have a Morita invariant, you have Morita invariant Hochschild homology. Now there's a generalization of this to the context of many objects. So now let's go, our model category needs to be a little bit nicer. If you want to know what sort of conditions you need for this niceness, you can either look in our paper, or the conditions are really coming from work of Lene Moser, a paper she published in HHA a few years ago. But still, there are plenty of interesting examples which this works. Special sets, chain complexes, metric spectra, many others. So when you're doing many object generalization, instead of considering a monoid in your model category V, you're going to be considering a V-enriched category A. So all of the morphism sets are actually going to be morphism objects in the category V in this context. And the notion of an AA bimodule is replaced by thinking about what can call it either a V-enriched profunctor, or it's actually a V-enriched functor from taking the tensor product of the opposite of a V enriched category A and a V enriched category B to V itself. That turns out to be the appropriate generalization of the notion of bimodule. And this gives us a way of generalizing the category ring V to a category called cat V, where now the zero cells are going to be appropriately cofibrant V-enriched categories, and the morphism categories are going to be homotopy categories of bimodules like this. And this notion of Hochschild homology generalizes to Hochschild homology of V categories with coefficients in V bimodules. And we can again restrict the case where the bimodule is just coming from A itself. So in that case, you have A up tensor A to V. It's the functor that just takes pair AB rather to its morphism category, morphism object. So in this case, there's this nice many objects generalization. And this is where I can actually formulate the notion of what's called agreement once we have this generalization. So it turns out that in this case, just as in the case of ring V, we end up with a shadow. And what's interesting to see is that even though here we're starting with V categories, the target of this shadow is actually the homotopy category V itself. It's not going to be the homotopy category of V cat. So we again have a shadow with coefficients in the homotopy category V on this many objects generalization of the category ring V. And the agreement result says that anytime I have an object here, so a monoid in the category V whose underlying object in V is cofibrant, and I compute its Hochschild homology, I could also compute the Hochschild homology with respect to V cat of the category of, this is some appropriate version of a category of perfect modules over the category A. And it turns out that these things are actually equivalent. So this is a generalization of a well-known result that one has, the categories of chain complexes and so on. So, and again, this generalizes the result that was proved when V is spectra by Campbell and Ponto. Okay, one final general remark about Hochschild homology theories, just to say why Hochschild homology is really the prime canonical example of a shadow. So this is based on work that was started by John Berman, in which I worked with Nima Razek. So I talked about Hochschild homology of monoids in monoidal model categories, or for V categories themselves, but you can actually also develop a theory of Hochschild homology for bicategories, such that we'll just call bi-HH, which is a generalization of what we've seen before. And it turns out that if you have a bicategory, then there is a shadow on V, which has coefficients in its own bi-Hochschild homology. So here we have let's just say you have a bunch of functors from these endocategories BAA, all with targets in this category, which is the bi-Hochschild homology of this bicategory, which is universal in the sense that for any category C, the category of, I've just written it as a set of, but there's actually a category of shadows on this category B with coefficients in C. There's actually equivalent to the category of functors from this category by B to C. So there really is there is some notion of Hochschild homology, which is the universal shadow for any bicategory. Okay, continuing on, let's get back to the world of equivariance. So the reason we made this detour talking about this very general context with shadows and everything, it's like, well, if we have shadows, then we know we have meridian variance. At least we know we have agreement as long as we're working with a nice enough monoidal model category. Can this give us what we want in the equivariant context? So that we can say, oh, well, the equivariant theory we were looking at before is just an example of this very general notion of Hochschild homology, and therefore, bingo, we know we have meridian variance agreement, everything we want. Doesn't quite work that way, as we'll see, but still, things are pretty much okay. So how can we encode cyclic actions in a general context? So let's suppose we're in a context where we have a nice monoidal model category, and let's consider the category of functors from, so this is the, when I write VC infinity, this is the category where I've categorified the group, the infinite cyclic group. That is to say, I've got one object and then a whole C infinity of morphisms. Another way to think about it is that the objects in this category are objects in V equipped with an automorphism, which corresponds to the image of the generator here. So here we have, this is, I think, a straightforward way to think about it, pairs like this. And in the case where V is the category of orthogonal spectra, and if we have any orthogonal CN spectrum, for any generator of CN, because G is actually going to give us an automorphism of X, and we can think of the pair XG as an object in SP aught. So this is how we can sort of make the connection. It's a way of sort of taking a step back from thinking too much about all the group structure and everything. Let's just focus on the fact that this is giving us an automorphism. And now we can think about this category more generally of objects in a monolithic category V equipped with an automorphism. So it turns out that if this guy, since this guy, or rather, if this guy is nice, then this one is nice too. So this is the category automorphism. So we have the same tensor product as in this category, and the unit object is obviously the unit object, and the automorphism you take is its identity. This category is also nice, which implies that we can apply all the machinery I just talked about, and we have a shadow with coefficients in this, the homotopy category of the aught, that associates for any monoid in this category. So it's going to be a monoid equipped with an automorphism, which is a morphism of monoids. And then we have any bimodule there that associates to it some object in this homotopy category. So in particular, we could apply this to the case where V is a category orthogonal spectra, R is some orthogonal ring spectrum, which I CN ring spectrum, which I can then think of as a ring equipped with an automorphism. And so that I can certainly compute this Hochschild homology, which would give me another spectrum equipped with an automorphism. But it turns out that it doesn't compute the right thing, because well, we'll see what the comparison is in a moment, but it turns out the coefficients are not quite right. This is really looking at the Hochschild homology of R with coefficients in itself, but when it really actually needs to include an additional twist. So what does this mean exactly? So suppose I have a monoid in V aught, and I have a bimodule over this monoid, all of this in the category V aught. So what this means, I have a picture where this is now an isomorphism, and I have isomorphisms here and here. I have this left action, the right action, and all of this should be compatible. That is being the structure of a bimodule in this context. And what I can do is use this automorphism phi of A to twist the action. So instead of considering M itself with lambda and rho, I'm going to twist the left action by phi, for example, apply phi first and then use lambda. Or I could equally well, I could twist with using phi inverse, which is also going to be an automorphism, and then apply the right action. And it turns out that this gamma, which is the automorphism with which M comes equipped, is actually going to give us an isomorphism of these two twisted bimodule structures as bimodules. That's one way in which you can sort of tease out what it means for something to be a bimodule in this context where you have objects equipped with an automorphism. And it turns out that what you really, if you want to do something, gives you a generalization of definitions I gave at the beginning of the CN twisted homology, then what you do is you say, well, let me take what I call the phi twisted homology of A with coefficients in this bimodule. And it's going to be the V Hochschild homology. So I'm dropping the V aught, the V Hochschild homology of A with coefficients in this twisted bimodule. And so if I just want to write the CR twisted homology of A itself, then I'd be taking coefficients in A composite phi. So this turns out to be the right thing to do. When V is the category of spectra, then the CN twisted Hochschild homology of R let's see, A became R here, sorry. This should be an A. The CN twisted Hochschild homology of A is then just this, this guy here in the case where the automorphism that you consider is coming from looking at the action of the generator. So we didn't get quite what we wanted, but all hope is not lost. It turns out that you still do have Morita equivalence in this context, even if it's not quite exactly what we were expecting. Do get Morita equivalence because of this. You indeed need to use this isomorphism. I said that the gamma in question was going to be an isomorphism between the action of phi on the right, or the twisted by phi on the left, or twisted by phi inverse on the right. But anyway, that's enough to enable you to get the Morita equivalence. You can still use a version of the Dennis-Morita-Waldhausen argument to get this isomorphism. But on the other hand, this does not underlie a shadow. There's a problem with one of the axioms that I didn't mention explicitly, the cyclic invariance axiom. So it's not really a shadow. So it's interesting to see this is an example of something which does satisfy Morita equivalence, but it's not exactly a shadow. It's almost a shadow. What consequences do we then get for this CN twisted Hochschild homology? Well, in particular, we're going to have Morita equivalence. If we have Morita equivalent orthogonal CN spectra, then their CN twisted topological Hochschild homologies are going to be the same. And it turns out that if you actually take the CN fixed points, then this is going to give you a shadow. The problem with the cyclic invariance, maybe unsurprisingly, disappears when you take the CN fixed points. So you weren't very far from being a shadow. As soon as you take fixed points, you get one. Furthermore, you can tell a similar story when you're thinking about this version of Hochschild homology for green functors. So this was this algebraic version where you're starting with green functors and with coefficients in Mackey functors, and that really it's always the same construction. It's always the cyclic bar construction. In this case, it's again going to be twisted by an action of the group. And so you're also going to get something that's not quite a shadow, but that does satisfy Morita invariance. And you do get an actual shadow when instead of taking CN fixed points, which doesn't make sense in this context, you evaluate at the subgroup, the CN itself. Moreover, another thing that we show is that there are these linearization maps that you can get by taking the homotopy groups of PHH to the Hochschild homology. And there's an analog of that for green functors as well. And these linearization maps are really morphisms of shadows. So there's a notion of what it means for something to be a morphism of shadows, and that gives you a nice way of comparing these different theories. Finally, if you actually have something that is a monoid in the aught, there's a way you can generalize the Dennis trace map. So if you think about what it means to be a perfect module over this object R phi, you'll see that it has something to do with thinking about sort of automorphisms over R phi. And there's the usual sort of Dennis trace map. You can go via automorphisms and then endomorphisms and use the usual trace map and end up here. And this gives you a generalization of the Dennis trace map, which then opens the door to using trace methods as well in this equivariant context. So thank you very much. And that's all I wanted to take today. Be happy to answer any questions you may have.